Okay, welcome to day 3. We're going to do the exact derivative of a function. First, we're going to go over some problems that we did last time. The approximate derivative, where we take x values that are really small. So here's my function. Here's my x value I'm using. So when I do f of 5, my result is 14. So I have the point 5 comma 14. Now I have to plug in h. So my new x is 5.1, and when I do f of 5.1, I get a result of 14.71. So 5.1, 14.71 is my point. And then my approximate derivative, f prime of 5 is equal to 14.71 minus 14 over 0.1, the h value, or 0.71 over 0.7. So f prime of 5 is about 7.1. Now I have this, so my new x value is 5.01. So f of 5.01 is equal to 14.0701. So I'm using these x's and y's. So f prime of 5 now, it's a little bit better approximation because I have a smaller h value. Every time I get a smaller h value, I get closer and closer to the exact derivative. So f prime of 5 is about 7.01. And this is what we did last class. And it's using a very small value of h to determine a derivative at a specific point. So what we're really trying to see is make h smaller and smaller, or what happens when h becomes 0. So these point B gets closer and closer to the original point A until they're on top of each other. And then we have the derivative at point A is the slope of the curve, or the slope of the tangent line. We're going to work on that today, slope of the tangent line at that point A. So now we're going to look at the exact derivative. What we did before with h using a very small value for h, 0.1 or 0.01, is close. So now we're going to do the exact derivative at a specific point. So I have to have the original function f of x. I have to have a number for x. This is important. And it's really just changing y over changing x. Except there's going to be more work that's going to be involved. So for this example, I have this function and this x value. So if I do f of 3, I get 9. So I have 3 comma 9. So now I have f prime of 3 equals the limit as x approaches 3 from this limit notation we had before of the original function x squared minus the y value I had, which is 9, over x minus 3. If I plug 3 in there right now, I would get, let's see, 3 would be 9 minus 9 over 3 minus 3. I would get 0 over 0, and I would be like, oh, that doesn't tell me anything. So what we need to do is factor. And when I do that, I still have my limit as x approaches 3 of x plus 3 over x minus 3 over x minus 3. And I realize that these cancel, and I have the limit as x goes to 3 of x plus 3, and now I can plug in this number 3. I get 6, so I have f prime of 3 is equal to 6. But I want to write my tangent line. So when I want to write an equation, I do y equals mx minus x1 plus y1. I figure these out at the beginning of the problem. Another word for slope is the derivative, so that's f prime or whatever number I want. So this x value was the given number, this y value is f of that given number, and the slope is f prime of that given number. So now that I have all those details, my tangent line equation is going to be y equals, my slope was 6, x minus 3 plus 9. What does this all mean? Well, if I would draw the graph of this, here is the graph of x squared, which you've seen before in your life. Right here is the point 3, 9. The tangent line would be this linear equation with a slope equal to 6. And that's what we're trying to do. We're trying to find the slope of the tangent line, or the slope of the curve at that given point, or the instantaneous rate of change. Well, this is going back to the problem we did on the front page where we use h was equal to 0.1 and 0.01, the same function. So I know my f of 5 was equal to 14. So now when I do my f prime of 5, that is the limit as x goes to 5 of x squared minus 3x plus 5 minus 14 over x minus 5. This is basically y2 minus y1 x2 minus x1. So I know when I plug in 5, I'm going to get 0 over 0, so I'm going to just do the equals the limit as x goes to 5, and I'm going to clean this up algebraically. And again, if I plug 5 in here, I'm still going to get 0 over 0, so I need to factor it. The limit as x goes to 5 of x plus 2, x minus 5 over x minus 5. I get to cancel some things out, because you know when you do this correctly, you better get something to cancel out. So I have the limit as that goes to 5 of x plus 2. I plug that in there, I get 5 plus 2. So f prime of 5 is equal to 7. We saw that on the previous page, that we're always getting closer and closer to 7. Now when I went to my tangent line, I have my slope, I have my point of 5 comma 14, so y equals 7, x minus 5 plus 14 is my tangent line equation. So we have established the approximate derivative by using small values for h, and then we did the exact derivative at a given point. Now we're going to find the exact derivative at any point x, not just a given point, it could be any point x, or what we call the general derivative. And we're going to use that same formula that we did before for rate of change, and I made you do a lot of times last year. I said we're going to add this little limit as h goes to 0, because we talked about that earlier. We want to know what happens as h becomes smaller and smaller and smaller, or better yet, h goes to 0. So I have to do this whole f prime of x equals the limit as h goes to 0 of x plus h squared minus the original function x squared all over h. Remember, we are putting in x plus h for all the x's. I still have this limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. Now I get to cancel out some things. Anything without h will not cancel. I still have my limit as x, see I keep on saying x, as h goes to 0 of 2xh plus h squared over h. One h cancels out here and here and here. I get the limit as h goes to 0 of 2x plus h. So the answer of 2x plus h, I'm going to get rid of this for a second. When I had you do rate of change, you kept giving me results something like this, 2x plus h. But now we're finding the derivative, so I have this limit as h goes to 0. That means every time I see h, it equals 0. So my final result, and notation does matter. I want to see notation. Don't tell me 2x. It's f prime of x is equal to 2x. On the previous page, don't tell me 7. Tell me f prime of 5 is equal to 7. I want to see the good notation. I will take off points for bad notation. This is the derivative at any point. So again, here's my graph of x squared. And if I took any point on this graph, let's say I took this point right here, 1, 1, then this slope here would be twice the x value, so this slope would be 2. If I took this point right here, negative 2, 4, then this slope right here would be twice the x value, so this slope would be negative 4. And the best case that we want to look at is right here at 0, 0. This slope is 0, and we'll talk about how important that having a slope of 0 is. Okay, this one is just more algebra work, but it's the same idea. Every time I see x, I'm going to plug in an x plus h. So f prime of x is equal to your limit as h goes to 0. Don't forget about that guy. 2 x plus h squared minus 3 x plus h plus 4 minus the original function. So I put it inside parentheses. All over h equals the limit as h goes to 0. Well, x plus h squared we just saw, I multiply by 2, I get 2x squared plus 4xh plus 2h squared. Distribute this negative 3. Distribute this negative. And here is my favorite step. Everything in the numerator that does not have an h will cancel out. And I know these guys don't have h's, so they all have buddies. Negative 4 plus 4 plus 3x minus 3x minus 2x squared plus 2x squared. What do I have left over? The limit as h goes to 0 of 4xh plus 2h squared minus 3h all over h. So those 9 red terms I had in the numerator, 6 of them canceled out. And now I can cancel out 1h, 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 1h. And I have the limit as h goes to 0 of 4x plus 2h minus 3. And I know this h goes to 0. So I have 4x minus 3, but I want notation. F prime of x equals 4x minus 3. This is what I want to see at the end. Now for this problem, I could go back and what I did on the previous page and use the exact derivative for a specific point and did that process, and it would work. But I want to find the general derivative first, and I'm going to use this idea, and I'm going to be able to do everything I want. So using the general derivative, I get f prime of x equals the limit as h goes to 0 of x plus h squared plus 5x plus h minus 4 minus the original derivative all over h. I can expand this guy out. The limit as h goes to 0, x squared plus 2xh plus h squared plus 5x plus 5h minus 4 minus the original function all over h. I get these last 3's all have buddies, they don't have x's in them. The limit as h goes to 0 of 2xh plus h squared plus 5h all over h. I get 1h to cancel out everywhere. I get the limit as h goes to 0 of 2x plus h plus 5. But then I know that this h goes to 0. So I get 2x plus 5. So right now I have f prime of x is equal to 2x plus 5. And that's a good start. This is my general derivative. But I want to be able to refine the tangent line. I want to write this linear equation. I want to write y equals m x minus x1 plus y1. Well, I need an x1, which I'm given, of 3. I need a y1, which is going to just be f of 3. I need a slope, which is just going to be f prime of 3. So f prime of 3 is pretty easy right now. So f prime of 3 is equal to 11. Now when I want to do f of 3, I just do 3 squared plus 5 times 3 minus 4. I get f of 3 is equal to 20. And when I'm all done with everything, I can just write my tangent line is y is equal to a slope of 11, x minus 3 plus 20. That is my tangent line. Okay, I'm going to go over notes in class today, so this is pretty easy, and you should be able to do the daily assessment. Thank you for watching this video.